Welcome to chapter 6, circular motion and Newton's application. This chapter is extended from the previous two chapters, whether into the motion of the circular motion, you did learn about it, and this part may introduce some influence of Newton's force for explain about that circular motion in terms of force. Let's see what we can extend from the previous knowledge. As I already explained about the uniform circular motion happen, if you consider about the particle that moving along this part, one reason that it can be moving like this because some of the inward point acceleration, because you change the velocity direction here, there's gonna be some acceleration pointing downward, and this is due to the force on the string tension, or maybe due to this lady arms is pulling this object to moving in a circle. We will name this type of force as a centripetal acceleration that linked to the mass and going to be the centripetal force, right? Because if you know the tangential velocity in the uniform circular motion, the uniform mean your absolute v is constant, right? So when you square up over r is the acceleration pointing inward to the center of motion, and when you know the acceleration multiplied by m, you will get the force. That is how we call the centripetal force that I said. What is the centripetal force? It is the force that pointing down, pointing in the backward of the vector r direction. R is the vector that point out of the polar unit, right? You have r for pointing out for this radial direction. So what happens when the string tension is broken? It's no longer moving in a circular motion. Now it's going to move at a straight line. Not link, straight line. Because no pulling force or the centripetal force. Right. And this relation you already know, because you know the AC equal to V squared over R if you look only in the magnitude of it. But if you consider it as a vector, don't forget that the direction of the centripetal acceleration or centripetal force is pointing toward the central of the circular motion. Let's look after in this, for example. As I said, we introduced this chapter is not only depend on the circular motion. We will try to explain all the influence of the Newton's law into this circular motion. So what if we would like to express about the v, the tangential velocity? So think about this is kind of like a conical pendulum, and this thing is rotated around this, like this. We would like to determine v. How about it? It's not swing like a pendulum, but it's oscillate or orbiting around the central. We point out like around this central here, and particle is orbiting around. And with this, if object have mass m over here, we can look after free body diagram. We have the mass m and mg pointing downward, right? We have string tension to pull it, to make it like a conical motion. This is string. And if you determine, you have the components here like your x and y, you can break the t components to upward and parallel. Since you know this angle here, theta, right? This means this is also theta. This is your t cos theta, and this is your t sine theta. So now I will try to look after this, and what causing this moving as a circle is because of the centripetal force pulling downward here. This is the centripetal force. So the t sine theta here is also the centripetal force. That the reason this object is still moving in a circle like this. So now you can check on this is what happened if you determine in terms of the second law of Newton's in x direction. What you have the your centripetal force, or t sine theta, equal to MAC, which is your MAC is V squared over R. That is the source that you can determine V. How about the V? And how in y direction? You have nothing moving upward or downward in this case. You have a constant motion with this string length L. And what you can see, like when you revolve this, you revolve with a constant speed. So this is still in the uniform semicircular motion. If you look up from downward, you see like this look like circular motion of this object, right? So from y direction, you will use the first law of Newton. So you have t cos theta equal to mg in this case. Now you got the information of t sine, t cos, mg, v square r. You said this is your equation 1. This is your equation 2. You can have the equation 1 over equation 2. Have them divide each other. So what you can get, you get t sine theta over t cos theta equal to mv square over r, that over mg. That get thing that you don't want out. So finally you get tan theta equal to v square over rg. If you would like to determine the v, your v is rg tan theta under the square root in unit of meter per second. As I said again, most of I show you in the example is derived in a generalized form. But if you would like to get the value in, you can substitute in and do a calculation, and you will find this more in the near future, right? But as you can see, we know the information of the length and r. We rather write r like this, or we can substitute the L information as well. Because from this, you can see the triangle here is the triangle like this with the theta, L and R, right? And with this case, you will see the form of the ratio between L and R, right? Because from this triangle, if you write it carefully, your R over L is sine theta. You can write L sine theta that equal to R as well. You can sub this into this term, so finally you can get V equal to root L G sine theta tan theta. You can also write like this as well if you want, but it's already finished if you can replace all this information and explain what is happening of this conical pendulum motion, right? This is how you determine the velocity or the constant speed around the tangential path of this motion. How about this one? This is still another circular motion that has the mass m attached with the string, and this is 0.5 kilogram. The chord distance is 1.5 meter. If you would like to determine the velocity here as well, what is the maximum speed at which the ball can be wired before chord break? So it's like the critical tension, right? You have to determine the V that large enough so that this still can be remain. So look after the assumption the string remain horizontal during the motion. This is only happen in the horizontal plane. If you said this is y, this is x, this only happen in x plane direction. Or if you thinking this as a 3D motion, you can rewrite like on this plane is your x, y, and the upward is z direction. There's nothing happening on z. This is only on x, y plane here. This is your x and y. When you look from the top view, this is from the side view. This is the top view. So let's see how can we find the maximum speed of this ball. The information that we know that the force that happen when this particle moving, if you look after the mass m here, there would be some centripetal force that happen on the string tension, right? Pulling it outside, and this is moving as a circular motion. So in this case, you will have your T as your centripetal force is equal to mv square over r. If you know the withstand maximum tension is 50 newtons, so that is your maximum T. So you sub T equal to 50, and m is 0.5 kilogram, v square is what you want, and r is 1.5. So finally you're gonna get v equal to square root of 1.5 multiply 50 over 0.5, and that is what you get in the final. The velocity in this case is 12.2 meter per second. It is the magnitude of the velocity or the speed here. If you said it correctly, is tangential one. Tangential speed because it's in a parallel pattern. It's not pointing this direction. My fault. It's pointing this because this is kind of like a motion represents. So with the constant v, that means this is still in uniform circular motion, right? As you can see, the link of this chapter is about introduce force in to explain about the circular motion, which is from the previous 2D motion. We ignore to state about the force, but we look after the acceleration of v square over r as the centripetal acceleration. So let's look after the next example. So this example, you have the mass of the car for 1,500 kilogram and moving on the flat horizontal road and with the curve like this. So problem is you would like to find the maximum speed of the car that can have then still turn successfully. This means when you have the velocity or the speed along the path at a circular motion, this car is not slip out. And only the reason it can track like this because some friction, and this friction is the centripetal force. So with this relation, you can see if you said this is your y-axis, this is your x-axis, the friction or the centripetal force try to pull this object to be steady at this position while it's moving. It's not slip out of the road path. So from this, if it's known that the radius of curve is 35 centimeter, that means with this corner you have the r is 35 not 3.5, sorry, 35 meter, and the coefficient of started friction and dry pavement, the mu s here, mu s is 0.5. So you would like to see what is happening and determine the v. Start with the second law of Newton's, which is you already know. What is happening force here is the centripetal force, which is the static friction. When you look after this frame, there's no moving toward this side or this side. Balance of this is equal to ma, which is v squared over r. And with the friction here, you link to mu n, or you know that from this is when you're looking after only x part. And if you look after y, you will have the upward and downward inequally, so the n is equal to mg. Next, I will go quicker and may not write this part because since we look after it, we know already that n equal to mg in the flat surface, right? In this case, I will sub n to this first. So now what you're gonna get after this, you have mu mg equal to mv squared over r. So as you can see here, I can write this part and move to this part quicker if I have the experience of calculate on this from the first law of Newton, right? We can get rid of m of each other. If we like to determine v, we can rearrange the term v squared to mu gr, so that your v is equal to square root mu gr, and now you sub everything in. Please use g equal to 9.8 as usual. So we will sub all the information in as this mu is your mu s, right? Your mu s. Some may ask like, why not using mu k in this case? Because this object moving on this part only, and it look like it stays still along x-axis. There's no acceleration toward this part. Only this happen is the centripetal force to maintain or make this object moving as a circular motion. This car moving as a circular motion. So you got the v equal to square root mu is 0.5 and g is 9.8 and r is where is the r? 35 meter. Finally, you're gonna get the velocity equal to 13.4 meter per second. This is the velocity, the maximum velocity that you can have to turn this corner successfully without any slip out. You don't want to have your car skirt out of the pavement. You want to make it stay on the uh, road track.